There's a spacecraft right now at this exact moment traveling through territory that no human instrument has ever mapped, detecting things that no model predicted, and sending data back to Earth that scientists are still struggling to explain. It launched in 1977. It is powered by the heat from decaying plutonium, generating roughly the same electricity as 3 Christmas tree bulbs. Its onboard computer has less processing power than a modern digital watch. And yet Voyager 2, the only spacecraft in history to have flown past all 4 outer planets, is now doing something no mission was ever designed to do. It is sampling the space between the stars directly in real time. And what it is, measuring at the edge of our solar system and beyond, is forcing NASA scientists to reconsider assumptions that the field of heliophysics has held for decades. The plasma is hotter than it should be. The magnetic field is aligned in ways that theory says it cannot be. The boundary between our solar system and interstellar space is not where the models placed it, not the shape the models predicted, and not behaving the way any simulation anticipated. And buried inside the 5 papers that NASA published simultaneously in November 2019, describing what Voyager 2 found when it crossed the heliopause, the official boundary of our solar system, was a detail so unexpected that scientists at MIT, Johns Hopkins, and the University of Iowa spent months debating whether their instruments had made an error. They had not made an error. The solar system's boundary is leaking, and what is leaking through it, in both directions, is changing what scientists believe about the shield that has been protecting life on this planet for 4 billion years. To understand why what Voyager 2 is detecting is so significant, you need to understand what the heliosphere actually is and why it matters. The sun does not simply sit in space and shine. It continuously exhales, a constant outflow of charged particles called the solar wind, blasting outward in all directions at speeds between 400 and 800 kilometers per second. This solar wind inflates an enormous bubble around the sun, pushing outward against the surrounding interstellar medium, the thin plasma of gas and magnetic field that fills the space between stars. The boundary where the solar wind's pressure exactly balances the pressure of the interstellar medium is called the heliopause. Everything inside the heliopause is the heliosphere, the sun's domain, its sphere of influence, the bubble that contains every planet, every moon, every asteroid, and every comet of our solar system. The heliosphere is not just a conceptual boundary, it is a physical shield. High-energy cosmic rays, charged particles accelerated to enormous energies by supernovae and other violent events throughout the galaxy, bombard the outer heliosphere continuously. The sun's magnetic field, embedded in the solar wind that fills the heliosphere, deflects and scatters a significant fraction of these cosmic rays before they can reach the inner solar system. Without the heliosphere, the cosmic ray flux at Earth's surface would be dramatically higher. Some researchers have proposed that periods in Earth's geological history when the solar system passed through denser regions of the interstellar medium, regions that compressed the heliosphere significantly, may have coincided with elevated cosmic ray exposure at Earth's surface that contributed to biological mutations and mass extinction events. The heliosphere, in short, is the reason complex life on Earth was possible. And Voyager 2 just revealed that it is not what scientists thought it was. When Voyager 2 crossed the heliopause on November 5, 2018, it was carrying 5 working science instruments, including, critically, a plasma science instrument that its twin Voyager 1 had lost to a mechanical failure in 1980. This made Voyager 2's crossing the first ever direct measurement of the plasma environment at and beyond the heliopause. Voyager 1 had crossed the boundary in 2012, but without a working plasma instrument, it could only detect the crossing indirectly, through electron oscillations during solar eruptions. Voyager 2's crossing produced the first direct plasma data ever collected from the heliopause and the interstellar medium beyond it. And within hours of the crossing, the data coming back to Earth was surprising the scientists who had spent their careers building models of what that environment should look like. The crossing itself happened in less than 1 day. The boundary between the sun's domain and interstellar space, an object roughly 18 billion kilometers from the sun, the product of 4 billion years of solar wind pressure pressing outward against the galaxy, is not a gradual transition zone. It is an abrupt wall, crossed in less than 24 hours of spacecraft travel. The electron density surrounding Voyager 2 jumped by a factor of approximately 20 in that single day, from the sparse, hot plasma of the outer heliosphere to the denser, differently structured plasma of the interstellar medium. And the temperature on the interstellar side of that wall was wrong, dramatically wrong. The models that heliospheric scientists had been working with predicted interstellar plasma temperatures of roughly 15,000 to 30,000 degrees Celsius just beyond the heliopause. What Voyager 2's plasma instrument measured was approximately 30,000 to 50,000 degrees Celsius, between 2 and 4 times hotter than any simulation had predicted. This is not a measurement uncertainty. The The plasma science instrument on Voyager 2 was calibrated, functioning correctly, and cross-checked against the indirect measurements available from Voyager 1. The interstellar medium immediately beyond the solar system's boundary is running at temperatures that the best heliospheric models failed to anticipate. The source of that excess energy is not fully understood. The leading hypothesis involves magnetic reconnection, a process where the magnetic field lines of the solar wind and the interstellar medium, compressed and distorted against each other at the heliopause, snap together and realign, releasing stored magnetic energy as heat and particle acceleration. But the mathematical models of magnetic reconnection at the heliopause scale do not produce enough energy to account for the full temperature excess that Voyager 2 measured. Something else is contributing. What that something is remains one of the open problems in heliophysics. The magnetic field discovery was the result that most directly challenged existing theory. Both Voyager 1 and Voyager 2 found that the magnetic field in the region immediately beyond the heliopause is oriented parallel to the magnetic field inside the heliosphere. The two fields, on opposite sides of the solar system's boundary, are pointing in the same direction. Result, confirmed independently by two spacecraft crossing at completely different locations separated by billions of kilometers, is not consistent with any standard model of how the Sun's magnetic field interacts with the interstellar magnetic field. Pre-Voyager models predicted that the interstellar magnetic field would be oriented at a significant angle to the solar wind's field, tilted by the structure of the local interstellar medium and the Sun's motion through it. The confirmed parallel alignment at both crossing points requires either a local interstellar magnetic field geometry that no previous observation had measured, or a process at the heliopause that is aligning the two fields in ways that existing magnetohydrodynamic theory does not predict. Leonard Berlanga, a physicist at NASA's Goddard Space Flight Center who has worked on the Voyager magnetic field data for decades, described the alignment as unexpected and not yet fully understood. It has been 4 years since that statement, and the understanding has advanced but not yet reached completion. The leaking boundary is the discovery that carries the most immediate implications for Earth. Among the 5 Nature Astronomy papers published in November 2019, one specifically addressed what Voyager 2 found about the permeability of the heliopause. Solar particles, ions from the solar wind, were detected by Voyager 2's instruments on the interstellar side of the heliopause, 100 million miles beyond the boundary. The heliosphere was leaking solar material into the interstellar medium through the region where Voyager 2 crossed, which is located at the flank of the heliosphere rather than at the nose, the front of the bubble facing the direction of the Sun's motion through the galaxy. Voyager 1, crossing at the nose, had detected almost no solar material leaking outward. The flank is significantly more porous than the nose. This asymmetry was not predicted, and its implication runs in both directions, because a boundary that leaks outward also admits inflow. A more porous flank region means that cosmic rays, energetic particles, and interstellar neutral atoms can penetrate the heliosphere more easily from the sides than from the front. The cosmic ray environment inside the heliosphere, including the cosmic ray flux that reaches Earth, is not uniform in all directions. The protection the heliosphere provides against galactic radiation is stronger at the nose and weaker at the flanks. And how much weaker depends on how the heliopause's permeability changes during different phases of the solar cycle, a question that is currently being investigated using data from Voyager 2 combined with data from NASA's IBEX satellite, which measures energetic neutral atoms flowing into the heliosphere from outside. The heliosphere itself turned out to be significantly smaller than models predicted. Before Voyager 2's crossing, the most widely used heliospheric models placed the heliopause at a distance of approximately 120 astronomical units from the Sun in the nose direction, with an elongated comet-like tail extending hundreds of astronomical units in the opposite direction. What the combined Voyager 1 and Voyager 2 data showed was a heliopause at roughly 120 astronomical units at the nose, consistent with predictions, but with the flanks significantly closer to the Sun than expected, suggesting a rounder, more symmetrical bubble rather than the elongated comet shape. And the interstellar magnetic field measured by Voyager 2, combined with data from the IBEX satellite's all-sky maps of energetic neutral atoms, indicates that the external pressure on the heliosphere is higher than models assumed. The interstellar magnetic field is 2 to 3 times stronger than pre-Voyager estimates, meaning it exerts up to 10 times more pressure on the heliosphere than simulations built on those estimates had accounted for. A heliosphere under 10 times more external pressure than expected is a smaller, more compressed heliosphere, a less effective cosmic ray shield. The implications for the history of life on Earth and for the long-term habitability of planetary systems in general are still being worked out in papers that continue to be published in 2025 and 2026. Voyager 2 is currently at approximately 143 astronomical units from the Sun, moving deeper into the interstellar medium at roughly 15 kilometers per second. Its power output continues to decline as the plutonium in its radioisotope thermoelectric generators decays. By 2025, the mission team had already shut down several heaters to preserve enough power to keep the science instruments running. The plasma instrument, the one that made the heliopause crossing so uniquely informative, is among the instruments fighting for power allocation. Each year that passes, the data Voyager 2 returns becomes more precious, because each year brings it closer to the point when its instruments can no longer transmit. Voyager 2 is approaching a region that models predict will show increasing plasma density as it nears the pile-up zone, where interstellar material has been compressed against the outer heliosphere for billions of years. No spacecraft has ever measured that region. Voyager 2 may reach it before its instruments go dark, and if it does, what it finds there will add one more data point to the picture that has been building since November 2018. A picture of a solar system boundary that is hotter, more magnetically complex, more asymmetric, and more physically surprising than decades of theoretical work had predicted. The spacecraft is still moving, the data is still arriving, and the terrifying truth. It has been revealing, confirmed measurement by measurement across 6 years of interstellar exploration, is that the shield protecting everything we have ever known is stranger and less understood than we assumed when we launched 2 spacecraft to go find out what it actually is. What makes the Voyager 2 story uniquely terrifying is not any single measurement. It is the accumulation of them, the way each confirmed result points in the same direction. The boundary of our solar system is hotter than predicted. Its magnetic field is aligned in ways that theory forbids. It is more porous than models assumed. It is rounder and more compressed than simulations showed. The external pressure on it is 10 times higher than pre-mission estimates suggested. Every measurement Voyager 2 has returned from the interstellar medium has been a surprise, and every surprise has been in the same direction, toward a picture of a heliosphere that is smaller, leakier. Scientific consensus of 30 years of theoretical work had established. That consensus was not careless. It was built from the best available data by the best available methods. What it could not account for was direct measurement, because no instrument had ever been there to make it. Voyager 2 went there. And what it found, confirmed in 5 simultaneous papers in the world's most prestigious scientific journal, endorsed by NASA, and continuing to generate new analysis in every year since, is that the protective bubble surrounding everything humanity has ever known and done and built is not quite what we thought it was. It is still protecting us. But the protection it provides, the size of the shelter it creates, and the forces it is holding at bay are all different from what science assumed for the 30 years before a 46-year-old spacecraft crossed into the dark and started measuring the truth.